Welcome everyone. My name is Angel Francisco Martinez. I'm a consultant here at Midas, and today I am presenting in collaboration with Luis Alberto Cruz from the University Autónoma Metropolitana in Mexico on his research study on the topic Why Perform a Soil Structure Interaction Analysis on Soft Soils. We're going to be looking at a comparison between what is basically the conventional or indirect method of soil structure interaction using springs used in point of view of a structural software, Midas Gen, and in comparison to the same building using the new integrated or direct method for soil structure interaction analysis, in which the soil is modeled from a geotech point of view, that is using solid elements, and this is using Midas GTS NX. So the main objective of the session is to compare the soil, one in case where it's a 3D solid element versus what would be essentially a 1D spring element. And we want to establish what is the difference between the setup of the two methods, as well as what are the key results for a soil structure interaction analysis. In both methods, the structure will be the same. It's essentially a 7-story building with a 1-story basement with a wall and slab foundation in what are considered soft soils. As we mentioned, the soil for the structural model will be represented by Winkler spring elements, whereas in the geotech model, the soil will be represented by 3D cube or solid elements. And in both cases, the nonlinear behavior is limited to the specific limitations of each. And we will be looking at some of the different combinations of or inputs for some of these parameters. And in the end, we will show that the results conclude that the traditional methods actually significantly underestimate the soil rigidity, and in terms of settlements produce almost half of the results as seen by the 3D solid elements. But we'll also inspect some of the structural results, like the moments and the axial forces are also being critically underestimated. So this research paper's focus is actually related to a local problem in the Valley of Mexico City. In this case, their main issues have to do with total settlement long term. There's almost like, I think the stats is like half a foot per year in some cases, as well as the differential settlements. And so they look at cases for improving these conditions in soft soils by either improving the foundation design, doing some sort of soil remediation, soil improvement, draining, as well as having to use what would be essentially deep piles. So when it comes to soil structure interaction analysis, the endpoint, especially when it's related to the geotech and a structural engineer, is to find the compatibility or to find a common value between what is essentially the raft and the ground deformations, in order to get the contact pressures and as well as some of the outputs for being able to properly design the foundations, in those cases being the shear forces, the moments, the axial forces, as well as the settlements. And there are 3 main methods for doing this. One would be basically closed solutions, hand calculations. The other one being using the stiffness matrix method, essentially the soil spring, the Winkler spring method. And then the third, the most difficult being, or the most complex, being the numerical modeling. And that's either by the finite element method or the finite difference method. Using the soil springs essentially requires that one gets and inputs what is the modulus of subgrade reaction. This concept was introduced back in the 50s by Terzaghi, and in this case, basically the raft can be modeled as either a 1D beam if it's a 2D analysis, or a 2D shell, or if it's a 3D analysis. And the soil itself is modeled by what could be either linear or non-linear unidimensional springs. And this behavior can, again, depending on the type of spring, but we essentially can estimate from the curve a value k of the stiffness when we graph what would be the load versus settlement in the curve. So from these kind of curves, loading conditions, we can get what is the coefficient of circuit reaction, the K value, and that would be essentially what's inputted as the stiffness for the spring. And there are suggested values for this. This is not a new concept, and so one can Google, or there are plenty of text available for structural engineers if they don't have access to lab reports or to a geotech team or company to help them. They can basically find these modulus of circuit reaction values for different kinds of soils from tables. But as you notice, there are pretty wide range of values for each of these spring stiffnesses. And so it becomes a little bit of either an iteration game. One has to choose more or less an initial value and run maybe a lower bound, an upper bound, and then try to see more or less based on that what they can get. Or ideally, if they do have, I guess, a direct report from the geotech team, then they have a smaller range that they can choose from. But I mean, these values, if they do have a collaboration with, or within the company, there's a geolab, or they have a geotech engineer who can run these tests, then they eventually run these play tests, and they can get what would be from the stress strain ratio for the nonlinear behavior, what would be the subgrid reaction module. And so there are also correction equations depending on the type of soil, as we see here for clay and for sand, that can be used for this. And over time, I mean, there were more advancements in the development of these formulas to have a more accurate representation of especially the nonlinear behavior. And you start to see towards the later years, there are more input parameters like Poisson ratio, elastic modulus, to get what's essentially a better approximation of this spring stiffness. So we see here the concept is going around the same lines. You have your structure, your foundation, depending on the type, and then the ground is essentially modeled by these springs, and then you end up fixing the springs in the degrees of freedom that are now corresponding to the direction of where the building or the load is being applied. However, some of the limitations are that for the most part, one ends up having a pretty similar value for the springs, and so it's not very accurate in terms of what's more realistic in the field, and that can, as we will see, turn into a limitation in some of these approximations, because the real value is going to be the soil is going to vary across the foundation. So as we were recapping, in order to find these solutions, there's the analytical method, some sort of hand calculation approach, the Winkler method, the spring method, which we will cover first, and then the numerical method, which would be essentially the counterpart using the 3D soil elements. Covering a little bit more into basically what these represent, these values apply to the K, or the spring stiffness. If we had an infinitely flexible foundation, then the spring would have no rigidity. It would be eventually a value of 0. However, if we gave it a very high value, let's assume something close to infinity, that it's almost like it's completely fixed, or a rigid foundation. And then, of course, somewhere in between is what we're now analyzing, which would be an elastic foundation. And so these rigidity parameters, or these stiffness parameters, are influenced by the geometry of the terrain, of the strata layers, if there's an inclination through them, the geometry of the foundation itself, some of the mechanical properties of the soils and foundations, steel versus concrete, if we are working on sand versus clay and such, and then of course the load distribution of the structure itself. Whereas with the numerical method, the two main approaches, as we had commented, are the finite element method, which is actually the one we'll be using today. And for this, just I guess some quick differences between this method and the other main method, which is the finite difference method, is the FEM requires an assembly of a stiffness matrix, whereas FDM does not. The calculation can be stopped by a singularity matrix, and during FEM, it can be used for static or dynamic analysis. And the dynamic analysis can be carried out by the two schemes, either explicit or implicit, which would be pretty helpful, especially when we're considering a structure, since we can also run what would be not just a time history analysis, but also a response spectrum analysis. We can also choose higher order elements for finite element method. And more importantly, these last 2 points, is we can consider complex 3D shapes, and we can take advantage of softwares that have friendly graphical user interfaces. That's a major contrast to FDM, whereas most of those softwares are code-based, so you have to know how to program. The shapes themselves of the meshes have to be limited to a base of 3D primitive shapes, and they cannot use higher order elements. All their calculations are technically dynamic. They just use very short time steps to consider what would be essentially a static case. And all calculations are explicit. So jumping directly into what we'll be comparing in today's study is on the left side, as we've been saying, this is the traditional model where the ground is modeled by springs with cave stiffness. This will be done in Midas Gen. The values we're inputting for the spring stiffnesses were obtained from one of the tables we showed earlier by Melly. This table was from 2001. But we'll see that there's going to be a variation in some of these reaction modules that correspond to different parts of the layers. Whereas in the full integrated model that we'll be comparing by direct method, this is where we'll actually be importing the full structure from the building software, Midas Gen, into the geotech software, GTS NX. We will be using constitutive models to capture the nonlinear behavior. For this particular case, we'll use more column, where the nonlinear behavior is captured by cohesion and friction angle. And we will see that these two softwares actually link up and can, in this case, import or export directly data as well as the full information of the structure. A little more details on the structure itself. This is what would be a 7-story building of reinforced concrete with a box excavated foundation. So 1-story foundation or 1-story basement. Here we have the materials, the values used for elastic modulus, Poisson ratio, and weight. And basically we have a series of columns and beams, the slab, and the basement wall dimensions. And we see here each of the stories and then more or less the dimensions of the structure. So pretty basic structure. We're keeping it simple, but mostly just to highlight what would be the difference in the formation of the base or the foundation. So starting with what would be traditional method, here's that same structure we were looking at on the slides in the program Midas Gen. It's a finite element software for structural analysis, similar to what would be the equivalent Midas Civil for bridges. So we can turn on the hidden view to show the full sections of the elements, but essentially we have all the details that we need, the same 7 stories that we had been looking at in the slides. So for this case, what we're gonna do is going to apply the soil springs onto the raft and then run the analysis to give it a quick inspection in terms of results before then exporting and comparing these results through the geotech software where we model the soil in 3D. So for modeling the soil as springs, we would apply them under the tab boundary. And we see here, this being a raft, we can apply them as surface springs. However, I'll just make a note that the software can also handle modeling and applying springs to piles. And this would be basically the essential input for such conditions. But in our case, we are only looking at, well, it's a flat or a raft foundation. So we'll use the approach of surface spring. There are different ways to apply these as well. They can either be distributed or point springs. We'll stick with point springs. And our element type, we see we can do planar, solid phase. We can keep it as planar. And the springs types, they can also be either linear, compression, or tension only. We'll do compression only, and we'll do in the negative vertical direction. And here's where I can apply the value, this K value we've been talking about, the modulus of subgrid reaction. And so for this case, we will just apply a value simulating what would be soft soil or sands. So we'll use 50 kips per feet cubed. And then to apply it to the model, there's different ways I can do this. I can either just do a side view and draw a box to select the elements, or I could have also selected directly from the worksheet. But if I go back to isometric view, we've seen that I've selected all the nodes related to the raft, and I can just click apply. The program has now represented these icons for the springs, and I can see also over here that under boundaries, the program has created these compression springs for all my nodes, and I would be able to inspect the values on these tables if I wanted to modify or give it a quick inspection for each of these values. So we see here the stiffness is applied to all the nodes throughout the raft. So that's step one. Step two would then be to provide support in the other directions. So if you recall, we were just applying these springs for compression only in the vertical direction. So what we want to do is actually apply springs that would be, or support for all the other directions, essentially fixing them. So we would come here and just say also, these are springs. You can see that by this method, it's a different kind of input. One can directly put these values in, but we can also essentially fix, and this is what we're gonna do, fix all degrees of freedom except for the vertical direction. And I will again just come to this side view and select the same nodes of the base slab, and just click apply. And we see that these linear springs are also updated here in the model. Depending on the loading conditions and such, the program does allow you to create your load combinations. So all the other details of the model itself for the structural component, we do have a, I guess, more detailed step-by-step explanation for that part, but we're going to focus on just the application of these soil springs or the foundation. So for this case, we would then be able to run the analysis and look at the quick results for that. So this case, having already had the analysis carried out with the same spring conditions, let's look at some of the results. So looking at something like would be your displacements, we would choose one of the load combinations that was created by the program. Under, in this case, the conditions we had were live loads and dead loads applied to the building, very simple. And we can turn on the legend, we can specify exponential or fixed degrees of freedom, and look at some of these results. It's a little crowded here, so I'm gonna try to expand this a bit. And maybe activate hidden again. So some of these values are quite small. I would change my units to inches just to keep kind of give it a wider spread. But we're looking at somewhere under an inch for max deformations at what would be the building. I'll go back and only look at the raft, but we can also look at some of the other structural component results, such as the beam forces, axial forces, or moments. So these are the moments, and then we can also look at the axial forces on the columns themselves. So here we're looking at about 395 kips max. Now to look a little bit more at the settlements directly on the raft, I can only activate the element of interest or the section of interest by going here to the work street and just tell it to activate. And now if I go back to my displacements, we can look at what's happening only at the raft. And with the top view, it's a little more clear what's happening. Again, going back to the inches. So we see it's a pretty small variation between where essentially the columns are versus the rest of the raft. We're talking about a fraction of an inch between them. And so that just kind of goes back to the spring not being able to properly capture any variation between what are the different parts of the raft as well as the load distribution. So now what we want to do is then export this full structure, or at least the superstructure component, to what is our Geotech software. And in order to do that, we would just have to, I guess as a suggestion to make this a lot easier, we see here that the raft has a pretty fine mesh, like a high number of nodes in the distribution. So that might be something that would be a lot easier to just redo within the Geotech software, and we can just focus on only exporting what would be the superstructure components that are going to be essentially the unable or more difficult to model manually in the other software. So we can end up just selecting or deleting sections of the element and only bringing it down to the core, which would be just the columns and the beams and the load combinations. So in this case, in order to facilitate the meshing integration into the Geotech software, we would modify the model in order to only have the beams and the columns. So let's quickly just open a model for that case. So this would be essentially what would be a good or a recommended variation for exporting the structure into the Geotech platform. However, if we wanted to give it a quick inspection and run it in this case, let's just compare if we had run this without any soul springs on the raft, but just as a traditional method of, let's say, applying fixed boundary supports to all the columns. And essentially, if we restrict any degree of freedom at the base and we ran this model, we would be able to verify that the reactions are equal to what would be the loads being applied. So if we take a quick look at that, looking at our reactions, let's take a look at the vertical reactions for a combination case and turn on the legend and the values. So we're able to see some of the reactions here in the range of around 76 tons for some of these elements. It's actually cutting off some of the values displayed directly, but we can see in the legend on the right what those values would be. And that, if we went back to the presentation and give it a quick inspection, these would be the values that we're getting displayed on the model. And essentially, we would just be kind of manually giving it a quick sum and verifying that this is equal to, we didn't show this particular step, but in this case, the structure had the following dead loads and live loads applied to it. And these values would, should and would do add up, or are basically the equal. So we verified that based on the weight and of the columns and the beams, as well as the loads applied, we have this equivalent load in tons, and that it's exactly the same that we're getting if we were to look at summing up all the reactions that we're getting in our columns. So once this verification is done, then we can be sure and export this superstructure to our Geotech platform so that we can then carry out the soil structure integrated analysis. So for that step, what we would do is we would just tell the program under the main menu that we want to export this format, MXT file. And we see here that in parentheses we see FEA and GTS. So that is the other platform, or essentially the format that the program can read in the Geotech perspective. And this is something unique to the family of Midas software. So this is the text file that is created with all the node information that would then be imported. Here's all the information about the beams and the loads and the distributions. And this can be then read and recreate this full structure with the section, dimensions, and everything in the Geotech platform GTS NX. So looking at that, if we were then now to open, this is the Geotech software GTS NX. We see it has a similar interface to what we were just looking at, Midas Gen, where what I mean is that there's like the work street, and most of the commands are based on the ribbon menu. And you can navigate it on the tabs at the top, and it groups almost like in AutoCAD everything that you need to that particular section together. The workflow would be basically left to right. You would first start off with your geometries, your 3D geometries or 2D geometries. Then you would proceed to meshing, where you would define the materials and the property sections. And then once everything is meshed, you would move on to start applying your boundary conditions, your constraints, and your loads, before then defining the analysis case, either stages, or as we will see here, there's actually multiple options for all kinds of geotech analysis. For ours, it'll just be a simple construction stage analysis, and then we see our results. Now, one of the differences that we were seeing or looking at, the focus of this session, of course, is that once we're in a geotech platform, defining the material properties are different than, especially for soils, than just the direct, spring stiffness. So let's just take a look at how you input these values in GTS NX. We would go here to create, and we see we have different variations, including interface elements, which we will be applying to the walls of the basement. And basically within isotropic, you see you have these main tabs where you define some values like elastic modulus, Poisson ratio, unit weight. And then we see that this model type we're looking at in particular is for elastic behavior. But if we wanted to look at something inelastic, nonlinear behavior, we would select from the list. In this case, we're sticking with more column. And the nonlinear behavior would be captured in this tab, as I mentioned, essentially through cohesion and friction angle. So it's pretty straightforward. We would just basically define, create, and input these values and create all our materials, and then just tell the program how these materials will be used. For instance, we would tell them some of the materials we'll define would be concrete, and they would be used for for the beam sections, which would be able to, we wouldn't have to manually input these values. We could just directly select from our DV either general sections, or we do have some standards that you can just select the section directly, and the program would update these values for you. And then the other things would be, you would tell the program some of this other concrete would be my shell for the raft, or the walls, retaining walls or basement walls. And then lastly, some of these other materials, the softer materials, would be for my 3D solid elements for the soil. So one of the, I guess, benefits of the software is you can also import from old models or from other models, either import all the properties of the materials. You can actually directly also import from Excel tables. So you can have one master table with all the materials and you can just directly import all those defined values. And then we also have a database that you can kind of select some values. If you don't exactly have some of the values on hand, you can just kind of choose from the list and such. So that's the quick intro into what is essentially defining the materials. In our case, we would be using or have manually imported these strata layer values. So we see we have the 5 soil layers, and these are the input values that we would be defining. So your cohesion, your friction angle, your elastic modulus, your K-naught value and such. So having manually, I won't go through this to save a little time, but having gone through these, either import from Excel or manually defining these values, we would then be ready to start the process of combining what is the structure with the 3D terrain to get this kind of final model look we see here with the 3D solid cube elements and each layer represented by a different color, having the values from the previous table. So let's take some general steps into how we can get to here, looking at the program. So the first thing we would do is import the structure from our building software. As we recall, this was a recent file we just created under the format MXT. We saw the text file, which I have here. So I would select that first. This should always be the first step when importing. And we notice here now we have the representation of the structure and we see some symbols. The base, we see that some of these symbols are representing what it's basically fixed boundary conditions. Here at the bottom, I can deactivate. Since my structure is going to be connected to the ground anyways, I don't need to fix the columns. And then some of the other representations we see here are related to the loads that were imported from the structure. So some of these load distributions were actually pretty hard to apply manually, but it is possible within the software because we do have the option for applying what would essentially be beam loads or beam moments directly to the elements on the software. But in this case, we have imported them directly from the other program, and we see here that some of the option loads that we have, we can also apply forces, we can also apply moments directly within the program. So the Geotech software does have a full capability to run a direct soil structure interaction analysis, including applying advanced loads on the structure itself. So we have the structure in place. Now we would be able to start modeling the terrain, and this can be done by a variation of methods. One can use a bedding plane function that we have, which would allow you to select locations and input all the information you would have about boring hole data manually and tell it at this location there's this plane, at this location there's this other plane. And as you go manually applying and generating multiple points, the program will interpolate and create the strata layers. A different method would be you can use also a grid phase. So you would be able to say, I have a grid of 11 by 11, and I could then be able to tell the program where this grid would be located, let's say the origin being this corner, the dimensions of that grid, and then you would be able to load an essential elevation distribution map. So these coordinates representing each one a location and the value being the elevation you would input, and you would be able to generate 3D terrains surfaces based on that. And then from there you would then just be able to have a solid, which would be something like this cube. You would center it, according to where you need the structure to be, and then use some of these other surfaces that you had created to divide up this cube, this solid, into your respective layers. So independently of how you do that, in this case our terrain is going to be flat, but the program also does have an option for being able to capture the topography using this terrain geometry maker. it's not really a focus of today's session, but just commenting that the program can read and extrapolate what is from essentially elevation contours, surfaces to create 3D detailed terrains. So in this case, just to save a little time, instead of going through all the steps by steps, we'll just import a finished 3D CAD file of the terrain, 3D ground. And we see here, obviously by its formation, we have it lined up exactly with where the structure is. I've already also divided this cube into my corresponding layers. And if I go here into the geometry tab, I can deactivate some of these layers to show that's going to be where the raft is excavated. And that's essentially where we would be extracting or creating the raft and the retaining walls from. You'll notice also that there are points corresponding to where the columns meet the raft. That's something else that would have to be done as a step. That's a very easy imprint command that we have here. That you would just basically be able to tell it imprint these columns into the ground so that my nodes match up between the 3D soil once I mesh with the corresponding location of the columns. Those nodes being shared, it means they can transfer information. So that's the geometry import in a nutshell, and the subsequent step would be we would be theoretically ready to mesh. We would want to give it a quick inspection in terms of what we call duplicates in this program. So basically making sure that the program recognizes that they are layers in contact. In this case, we see here that they are because they're shown up in orange. So this is a key tool for meshing in 3D that makes it so much easier to verify that your mesh would be properly connected. Had it not been, we do have a very easy auto connect command. You can just correct that in one simple step. So now we're ready to mesh, and we would, as we had mentioned before, have to import or define all the materials manually. What I can do is just directly import this. These sections were imported from my building, but I can do something similar and just import from a finished model all the rest of the layers that I need. So my raft materials, as well as my soil layers, I can bring those in. So these properties, now that they've been imported, have also imported the materials that correspond to them. So we see here our soil layers all are using more column. And if we wanted to give it a quick inspection, we can just double click and look at the values that were used for some of these. And we would be able to start meshing. We typically recommend you start meshing from the inside out. What that means is that you start with your smaller segments, and you can essentially just choose the sections of interest. You would assign the corresponding material layer to them, remember from the table, assign a value for the size of the element, and then here you can choose if it's a tetrahedral, essentially a pyramid shape, or what we call a hybrid, which is the cube shape. We can give this a preview of the values. Let's say maybe that's a little small, maybe we can go twice the size. And then just click apply here for, let's say, give it a name, like this is the excavation layer. And then just mesh them subsequently. This would be the other excavation, but this has a different material value. And then we would continue this, start meshing. Usually for the rest of the layers, we give it a larger value. So this would be, for instance, layer 1, and I switch back the materials. And we see that the program automatically, even though the outer dimensions of the mesh are bigger than the smaller original dimensions, the program has automatically now connected these different sizes to my corresponding layers. And we would continue this, so on and so forth, until we basically reach what is the final model dimensions. In this case, I'm also just kind of seeing here, we would finish the steps to mesh the rest, and sorry, not the right model. And I'll just open a model that's finished with the mesh, as we see here, in terms of the solids. And what would be ready to do now is look at more in depth to the structural components. So I'll deactivate all my layers except for these excavated layers. Sorry. And what we're gonna want to do is actually both of these. We're gonna want to extract what are the wall elements and the raft elements from our existing soils. So first you model the 3D terrain, and then you get into the structural components in case of the foundation. So for that, as I mentioned, we would use that extract command. We can either directly select from the meshes. That's a little tricky to capture all the elements, so it's easier to just activate the solids. These two, and tell it, for instance, I want to extract from this face what is first the raft, and the program has now matched the existing mesh, and then I would do the same for the walls. The basement walls. And I would just be sure to give it the other property. Recall that this is now not just material, but also property related to the thickness of each of these. Correct. So now that I have deactivated the geometry, we see here we have that structural component taken care of, the full structure with the walls and the raft. And then the last things would be to apply what are the boundary conditions to the soils. We were able to move on to the next tab here. Actually, we want our raft to have, or our walls to have interface elements, which are important for properly capturing the behavior between what is a structural component in a soil, especially when there's a difference in rigidity, like there is in our case, since we're dealing with soft soils. So I would select my wall. I'm gonna actually do it by the method of from a shell element, since this is a shell wall. I will do an interface on both directions. Select the nodes at the base. And we can use our wizard assistant. It's essentially the same as in Plaxis. This program, or this, will extract the local values surrounding soils and apply what is essentially the corresponding values for the interface. And we also want to create rigid links for our raft, since we're doing a construction stage analysis. And then once we've created that, we can then proceed to apply the boundary conditions and whatever other loading conditions that we need. So in this case, the program, we can apply the constraints and boundary automatically. And although it might have been imported as a load, sometimes it's good to just verify or reapply essentially the gravity load. We see here through this arrow. So now we would be ready to run the analysis or set up the analysis. We would go construction stage and set up our analysis stages. I'll open a finished model just to save a little more time here. So in this case, we see here we've created a construction stage analysis under stress. And the stages are as follows. We have the initial ground layers with the really rigid link that replaces the interface activated in stage 1. We apply our boundary conditions, our self-weight, and we define the global water level. That's just another big difference between the structural point of view. Is the springs you would have to modify, and it's really hard to actually or properly capture, especially if there's some sort of modification in the elevation level between the construction process. Stage 2, we then excavate the ground and install the retaining or the basement walls as well as the interface element. So for that case, we deactivated 2 excavation parts and the rigid link. Here I'm just clearing the displacement so that our final results are only related to the structural components. Third stage is activating or installing the raft, and then fourth stage is activating the full building, in this case denoted by the under the default mesh set, as well as the loads. And then we would just run the analysis, create an analysis case for construction stage analysis. Some variations you can say is consider the water pressure load and the rafts automatically, and if you wanted to have your K-knot condition of the ground. And essentially when we run that analysis, we would look at these results here given by stage, and we would be able to look at our displacements, our total displacements. I can easily change the units to feet or to inches. So we see in the other program we were looking at less than an inch. I can actually exaggerate the deformation here. Whereas here we're looking at more realistic values of up to 5 inches. And the program also gives us output values directly to the structural components, like the axial forces, and the moments. And of course, these would be compared directly to what would be the other approach. But the software does give you outputs just like you would see in the structural software. So going back to the presentation, here we have a very quick one-to-one comparison in between the 2 approaches. We're looking at a difference between what would be almost 2 centimeters versus 12 centimeters for the max values under the 2. So again, if I'm looking at the values here and I wanted to, let's say, isolate just the raft, I can also just deactivate, similar to what we did in the Gen platform. And then I can go and look at my, what would be displacements, maybe my vertical displacement. And here again, we were looking at it in the other software in the box in centimeters. We can do it here in feet or inches or whatever units we want. I can also directly ask it for its man mix, or I can probe values of interest to generate a table. Or lastly, I could directly also just extract and graph. So I could tell specific values of interest, let's say settlements. Let's say we want to go through the whole process and get the max values or the absolute max values. Let's generate one table for that. And this can be easily graphed within the program or just exported to Excel, as we saw there. Or we can also, similar to what we had done before, instead of selecting the max, we can choose nodes of interest. So we can choose 2 nodes in the center and then nodes around the corners and select for which stages, or if we only want at the very last stage where everything has been included, and generate its own table there. I'll reformat that. So we see here the location of the nodes and the values for each. So there's different ways within the program to extract these values that you need for your reports. So in conclusion, we've carried out the analysis in both techniques, both the traditional, aka indirect method, where we use the Winkler spring elements for the soil, and then of course we compared that with the exact same structure and loading conditions for the direct method or the integrating method. And we looked at in detail where the soil was modeled as 3D shapes. We seen that the 3D FEM model with the soils in solid shapes indicate that the settlements, total and differential, are higher in what would be obtained relative to the traditional method, as well as the bending moments and the actual forces are over twice what we were getting from our structural point of view. So it's, as we've seen, it's more intuitive, or more it's going to be more of a easy to understand, to see how this is happening for softer soil conditions. Of course, if you were looking at a structure in stiffer ground or rock, then this wouldn't really be too much of a concern. But especially the issue comes into a problem when the value of the direction models is going to be low, and it's hard to consider it. Usually it's considered like a constant value, apply a constant value throughout the piles or the raft, and you go with the lower end values just to be safe, which means you are consistently over designing your foundations. And so we see that, of course, there's a lot of theory into the constitutive models, but the more column failure or more column constitutive model is pretty well understood and pretty well accepted. I would say close to 70 to 75% of the cases in 3D geotech software for finite elements use more column to capture softer soils, compressible soils. And so this is a pretty handy tool. It's not too much beyond what the input values would be. And so in this case, we were looking just at a very short-term, I guess, what would be settlement analysis, but it's not really, I guess, looking at a long-term. Had we wanted to, in GTS NX, we could have done this for long-term settlement, considered it essentially a consolidation analysis, or we could have also run a true dynamic soil structure interaction analysis, which is really a more case of interest for our clients or our fellows in the Pacific coast, all throughout, all the way from Chile to Alaska. So just quickly kind of covering that aspect in the program, that while we were looking at, in this case, it was just a construction stage analysis, so it's not necessarily static. We could have also run this analysis for all these geotech point of views. So as we were saying, consolidation analysis, where we specify the duration of the settlement over time, and we can also have boundary conditions for draining over long periods of time, so we can get that excess pore pressure out, as well as what would be some sort of vibration analysis, eigenvalue, response spectrum analysis, or our seismic analysis, or time history analysis. So all this is possible with the structure and the terrain itself, and we, I guess, would be getting a lot more approximation or better results for those kind of soil structure interaction analysis that we could ever do with the spring elements. So that's the conclusion of the session. Are there any questions?